Greetings, welcome to lecture number 24 on basic circuit theory. I am Razavi. Today we will continue to look at inductors and their properties and understand how inductors respond to, for example, current inputs or voltage inputs as examples of very simple circuits. And then we will look at some other properties of inductors that also are interesting as far as circuit analysis and design are concerned. And finally, if we have time, we will begin to look at our first simple RL circuit to see how it operates and how we go about analyzing it. But before we go there, let's take a look at what we covered last time. So we started by introducing the concept of inductance and inductors, and we saw that the original observation by Faraday was that if we have a wire carrying a current and hence generating a magnetic field around it according to the right-hand rule, and if this current changes with time, which means the magnetic field changes with time, then this time-varying magnetic field can induce a voltage on a, for example, separate piece of wire. So if I place a wire here, this red wire, I can measure voltage here, even though there is no current passing through the red wire. So it's a fascinating effect, and it's certainly not Ohm's law. But then we tried to extend this idea, and we said that even if you have a single wire carrying a time-varying current and experiencing its own time-varying magnetic field, then that wire also must generate a voltage across it because of Faraday's law. So we would expect that a voltage will be generated here even though this wire has no resistance. So again, this is not Ohm's law. So this is something that we call self-inductance or just an inductor. And of course, a simple piece of wire will not be a very good inductor. So we typically wind it in some form, like what we saw last time in this form, that allows us to have more inductance for a given length or given volume, etc. So for such a device, which we call an inductor, we have a current, a voltage, and an inductance. And these three are related by this equation. The voltage that we generate across this inductor is proportional to how fast the current through the inductor is changing with time, multiplied by L1, of course. So this equation, of course, has to be observed with respect to the polarities that we have here. So if the current is flowing from high potential to low potential, then there's a plus sign here. If the current is going from low potential to high potential, then there's a minus sign here. All right, but this equation also tells us some interesting things about the behavior of inductors. For example, when there's a switching event going on, something wants to change suddenly, the inductor has a certain behavior. What we know is that if the voltage that is available for this inductor from the rest of the circuit is less than infinity, then this derivative has to be less than infinity. That means that the current through this inductor cannot jump instantaneously. And that's the key property of inductors. They resist the change of current. They don't want the current to change too fast. On the other hand, if we go to an extreme condition where the current through an inductor has become constant, so let's say this is inside a big circuit and eventually all the transients have died away and we have a constant current through the inductor, and then we know that the voltage across the inductor will be zero. And a device that guarantees a 0 volt difference between its terminals is a short circuit. So that becomes a short circuit. So these two cases are important to remember because they often happen in our transient analysis of circuits. Okay, and one last point was that the initial condition that we can specify for an inductor is a current through it and not a voltage across it. Fundamentally, it's the current through the inductor that can serve as what gives the inductor energy, and we will see that today. Remember, for capacitors, the initial condition was a voltage, because it's the voltage that gives the capacitor energy, 1/2 CV squared. So we will see something similar in terms of current and inductance and the energy stored in the magnetic field of this inductor. All right, one last point. Last time I said that this is an inductor, right? This is an inductor. And when I started out, I said this is not an inductor because it's just a piece of wire and it satisfies Ohm's law and so on. Now this doesn't seem quite to agree with what I just said here, right? So is this an inductor or is it not an inductor? We have to decide, right? This is a piece of wire. Well, strictly speaking, even a piece of wire has inductance. So the inductance from here to here is not zero, even though it looks like a straight piece of wire and even though it may have no resistance at all. But for our analysis, we assume that you have a piece of wire is ideal. It's like a short circuit. It has zero resistance and zero inductance. But if you want to build an inductor, then of course we wind it and all that, okay? Just to avoid any confusion. So in our studies, we typically assume that a straight piece of wire does not have any inductance or its inductance is negligible. All right, so let's go and look at some more examples of simple inductors. So here's another example that we have here. Okay, so last time we had a situation where we had a current source feeding an inductor like so. Call this I1 and L1. And we're trying to plot this voltage here, right, if you remember. And the current source was a ramp last time. So this time we'll make it a little more interesting. So suppose I1 looks like this as a function of time. So I1 as a function of time is 0 before time 0. And then it looks like a ramp. So it goes up for some time, and then at some time t1 it becomes constant, and then at some time t2 it falls linearly back to 0, okay, and it reaches 0 at time t3. So this is a current waveform that I have managed to generate by this current source. It's pushing this current through the inductor, and I would like to find the corresponding output voltage. Now I know that the voltage across an inductor is given by this equation, so I just need to take the derivative of this waveform to obtain the voltage. And of course multiply by L. So I will say that V out, the voltage across the inductor, is given by the derivative of all of this. So we see that before time 0, we have a constant value, is 0 anyway, so that's 0. At this point, we have a certain slope, so let's call that slope alpha. So this jumps to alpha times L, right? The derivative times L. And this slope is constant up to T1. From T1 to T2, the slope is 0. So the voltage across the inductor is 0. So this voltage jumps to 0. And then at T2, we have a negative slope, so let's call that beta. So this slope is multiplied by L to give us the voltage across the inductor. So now this will be like this. This value is beta L, and this goes on until T3. Okay, so this is the overall shape that we have. Now let's say that this goes back to 0 from here on, just for simplicity. So this also goes to 0 like that. So the voltage waveform across the inductor looks like this. All right, it's just a derivative of the current waveform that's passing through the inductor. All right, so that's simple enough. But let's try to see what happens as we go to some extreme case. If I make these transitions faster, what happens? So suppose this transition happens in a much shorter time, so something like that. And similarly, this transition happens in much shorter time, like this. So then what happens to the voltage waveforms? Well, they're proportional to the slope. So this voltage waveform, which is alpha is now much bigger. So this height will be greater. So it will be, for example, here. And of course, it lasts, let's say it lasts up to here, to this little time here. So it lasts for a shorter amount of time, right? Only from here to here. Past this point, the current is constant. And then this goes on up to right here, this point. And at this point, we're dropping at a faster rate. So the voltage is larger, but more negative. So the voltage will be like this. And this lasts up to this point here. So it goes back and stays at 0. So we see that as the slope of these transitions increases, the pulse that we have generated here becomes narrower and taller, both here and here. So in the limit, if this transition is infinitely fast, what do we get here? This becomes infinitely narrow and infinitely tall, so it becomes an impulse. So in the limit, if the current jumps here and jumps here, that requires that we have an impulse of voltage here and an impulse of voltage here. If the circuit surrounding this inductor over here is capable of sustaining an infinite voltage, then it's fine, we can do that. And in other words, if this current source really can do something like this, if it can jump from some 0 to some amount in 0 time, yes, we do get a very high voltage across the inductor. And in fact, this is a problem in some circuits that can damage some circuits, and we'll talk about that later. All right, so that was one little example. Let's go to another example and see what we have here. So suppose I have a voltage source, which we call Vin, and I have directly connected this to an inductor, L1, and I am interested in this current as a function of time if this voltage has the following shape. So let's plot Vin as a function of time. So our input or our stimulus is given by something like this. Vin initially is 0, before time 0. Then it grows linearly with time with the slope of alpha up to some point T1. T1, and then it stays constant past that point. All right? So this time I'm applying a voltage across the inductor. Previously I was applying a current through the inductor. And the voltage has a ramp section and then a flat section. And we would like to find the current resulting from this voltage input. Okay, so what we know is that the current, according to this equation, is the integral of the voltage and then divided by the inductance. So we have to integrate this. So let's say this is alpha t here. So we say the current I in is 1 over L1 integral of alpha t dt. This is for 0 to t1, right? So from 0 to t and for t between 0 and t1. That's the equation that we have for the current passing through the inductor in response to this ramp voltage. Okay, so that comes out to be alpha over L1 times t squared. Our assumption is that there is no initial current in the inductor. If there were, then we'd have to add that here, because that would be an integration constant that we would have to include. But right now we assume there's no initial condition. Okay, so this is the current waveform passing through the inductor between 0 and T1. So let's try to plot that for now, and then we need to see what happens after T1. Okay, so here we go. I have I in and then T. Okay, so this is a simple quadratic. So it goes parabolically up to this point T1. It goes up parabolically like this. Okay. So the current is growing relatively fast, right, parabolically with time. Okay, then what happens after T1? After T1, the voltage has become constant. If the voltage is constant, we have to integrate properly. So now, for T greater than T1, we say I in is equal to 1 over L1. So let's call this voltage something. Call this V1. So that would be V1 times T. Because I'm integrating V times dt, and V is given by V1 a constant value, so it comes out of the integral, and it just gives me T. So beyond T1, the current still grows, but now linearly with time. So we have an equation of this form. So this is a straight line and has a certain slope, which is V1 over L1. That is the behavior of the current that flows through the inductor. So one thing that is particularly interesting here is that the current through the inductor grows unbounded, right? It just goes to infinity. And that sort of makes sense. Does it make sense? Well, when the voltage is constant, it's like you have applied a battery across an inductor. And what should happen? The inductor wants to draw more and more current. So the current just keeps going up and going up, as if the inductor wanted to act as a short circuit, right? It's not entirely true, but intuitively that's what would happen. All right, so let's go on to another example to see what happens here. So let's change the color of our pen to green. Look at another example here. Okay, so in this case, we will consider something very simple. We have a battery, a resistor R1, an inductor L1, a voltage source VB, and we are interested to find this current here. Call it I1. All right, very simple. Our assumption is that this circuit has been connected like so for a very long time. So all of the transients have died away. There's no time varying component anymore. So if there are any currents and any voltages in the circuit, they're all constant. And we would like to find the current that flows through the loop under that condition. All right, so what do we do? Okay, so we say that if everything has become constant, for example, I1 has become constant, so we say I1 is constant. That means that the inductor voltage VL1 is equal to 0, right? The current doesn't change with time, so the voltage across the inductor is 0. If the voltage across the inductor is 0, how much is the voltage across the resistor? Okay, so this voltage is equal to this voltage plus this voltage, right? So this voltage is 0. The voltage across R1 is just the battery voltage. So this voltage here is just VB. And because I have the voltage across the resistor, I can find its current. So that means that I1 is equal to VB over R1. Okay, very simple. All right, the purpose of this example is to show you how we can create an initial condition in an inductor before we start doing something with that inductor. So if you wanted to create an initial current through the inductor, you would hook it up like this, through a resistor to a battery. You adjust the value of the resistor to give us the current that we need, or the battery and the resistor, right? And then this inductor is ready. It has a certain current in it. Now we can switch it out of here, switch it into something else, etc. And those are things that we'll see later. But this is a very simple example of creating a known current through an inductor. All right, let's go to another example and make it a little more interesting. So let me do this. All right, so we found this current in the circuit, right? Now I'm going to add a resistor here, R2. Okay, so we'll still keep this current, call this current I1, right, like before. And the question is the red I1 different from the green I1? Now that I have added this resistor R2. So we have to think about it and see. Again, we're assuming that the circuit was built a long time ago. All the transients have died away. Everything is constant. Okay, well, what we see is that because the current through the inductor is constant, whatever it is, it may not be I1, but whatever it is, constant, right? So we say current through L1 is constant. And again, this is because the circuit was built a long time ago and all these transients have decayed, have gone away, right? Okay, so if the current through L1 is constant, we know that the voltage has to be 0 across the inductor, no other way, right? So we say VL1 is equal to 0. If the voltage across the inductor is 0, how much is the voltage across R2? Well, that's also 0. They're in parallel. So then how much is the current through R2? That's also 0. So we say VR2 equals 0, which means current through R2 is 0. So this current is 0, this current is 0, right? This current is 0. Okay, if the current through R2 is 0, and this current I1 is coming in, where would it go? It cannot go this way. It has to go through the inductor, right? So because the current through R2 is 0, all of I1 must flow through L1. All right? And how much is I1? The red I1. Well, this voltage is still 0, right? If this voltage is 0, this side of R1 is 0, this side of R1 is VB. So the current through R1 is still VB over R1. So we say I1 is VB minus 0 over R1, right? VB minus 0 over R1. Okay, so the current didn't change. So even though I brought another resistor and placed it in parallel with the inductor, nothing really changed in the circuit as far as these initial conditions are concerned. So this is just because if we have waited a long time and the current through an inductor is constant, it forces a 0 volt difference across it. So it acts like a short circuit. So this is a short circuit, and if you have a short circuit here and place a resistor in parallel with it, the short circuit dominates, right? The resistor doesn't have any role in the current division between this and that. Okay, so that's an extension of that example. As you can imagine, circuits and electronics also have wide application in robotics. So here's an example that is quite interesting. In this paper, they deal with flapping wing robotic insects. So these are very small insects that are robotic, and they can travel to different places and collect information. For example, they can fly over a fire and collect information. They can go into the battlefield and collect information, etc. So they are very small and very light in weight. So here's a hand, and here's the flapping wing micro robot. So you can imagine this robot, of course, has to have electronics in it to be able to fly and to be able to collect information. In particular, for these wings to flap, they need a piezoelectric device that creates this movement. And for that, they need to generate a voltage. And that's how they come up with this circuit that takes a battery voltage from here and generates a high voltage that is necessary for the piezoelectric device on the far end. Now, there are a whole bunch of devices in here. We know some of them. We know switches and capacitors and inductors and resistors. We don't know these devices. These are called diodes. These are what you would study in electronics courses. But we can see that there's a great deal of what we have seen in this course in terms of the devices and the concepts that are also useful in an application like this. When we are trying to generate, for example, a high voltage from a low voltage or the other way around. So that is one application of electronics and circuits in robotics. Isn't that beautiful? Now let's go and look at another example here. So I have a battery, VB, I have a switch, and then I have an inductor, L1. And this switch turns on at time 0, and we would like to plot this current, I1. All right, so as you can see, the circuits that we are considering right now are very simple because we need to learn how to walk before we start running. And that's the objective of all these very simple situations. All right, so the switch is not conducting, is open, is off before time 0. So before time 0, there's nothing here. This inductor has no current, there's no life. Everything is 0, right? So the current is 0. This current is 0. So we say for t less than 0, I1 is equal to 0. All right, and then we turn the switch on. It starts conducting. Okay, so how much is I1 at 0 plus? So I1 at 0 plus. Well, we have to decide. Can I1 jump instantaneously from 0 minus to 0 plus or not? If the only way for I1 to jump is for this derivative to be infinite, is for the voltage available for the inductor to be infinite. Can this circuit deliver infinite voltage to this inductor? No, because this battery has some finite amount, 1.5 volts, 5 volts, something like that. So an infinite voltage is not available here, which means the current of the inductor cannot jump instantaneously, which means the current through this loop at time 0 plus is still the same as at time 0 minus. So that still has to be 0. All right? Okay. So, and then what happens? All right, so then there's a current flowing. We have a battery, a piece of wire, an inductor, and some current starts flowing. How do I calculate the current? Not a problem. I say from here, right? I say I1 is equal to 1 over L1 integral of VB dt. VB is constant, so that's just a VB over L1 times T. So what we see is the following. We see that I1 as a function of time was 0 before time 0. Right after 0, at 0 plus still has to be 0, according to the analysis we just did. And then past that point, it's just going up linearly. So it's going to go like this, right? And this is, of course, not that much different from this situation. Here we had a constant voltage across an inductor from now on, from T1 on. And of course, we saw a ramp for the current generated through it. Okay, so that's a nice little example that we have here. All right, so I think it's good to summarize our findings so far for some of the properties of inductors before we look at more properties. So we say summary. We say with a zero initial, actually let me erase this. I have to put it somewhere else. Okay, so here's the summary, and is a particularly a comparison I want to have between inductors and capacitors. So, all right, so let's see here. Okay, so we say inductors and capacitors. So there are 4 different cases, depending on whether we have an inductor or a capacitor, and whether the voltage or currents are changing rapidly or have stopped changing. They're constant. Okay, so those are 4 cases we want to consider. All right, so we say for inductors, we say if V is less than infinity, right? If the voltage that we can give to the inductor from outside, whatever it is, right? If the voltage that we can give to the inductor is not infinite, then the current through the inductor cannot jump instantaneously. So we say I can't jump, right? So if I is equal to 0 at 0 minus, it will want to stay at 0 at 0 plus. So I equals 0. And if the current is 0, what does the inductor represent? We have an inductor. The inductor says my current shall be 0 here, and it shall be 0 here. Right? That's what we decided. A device that wants to maintain a 0 current, what is it called? It's called an open circuit. So we see that the inductor is equivalent to an open circuit. All right, so just right around here, the inductor is acting as an open circuit because the current through it cannot change right away. Of course, past that point is different, right? Because now we are giving it time for it to change its current. But right around that transient, that switching event, whatever transition we have, the inductor acts as an open circuit, provided that it has a 0 current at time 0 minus. Okay, for capacitors, what was the situation? Well, for capacitors, it was the other way around. We said that if the current available for a capacitor is not infinite, right? So we have a capacitor, it's connected to the rest of the circuit. The rest of the circuit is not capable of giving it infinite current, then the voltage across the capacitor cannot jump. So we said V can't jump. So that means that if the voltage on the capacitor is 0 at 0 minus, it has to be 0 at 0 plus. So we say if the voltage is 0, it wants to maintain that 0 voltage for a little while. So it acts as a device that guarantees a 0 volt difference, and such a device is called a short circuit. So the capacitor is equivalent to a short circuit. All right. So these 2 cases correspond to situations where we have some sort of jump, some sort of transient, some sort of switching event in a circuit. And we're looking at the circuit just before that event and just after that event. And we're trying to decide what happens to the circuit. So these 2 are extremely important for those cases. All right. And then we have the other extreme case where we have waited for the circuit to settle. All the transients have died away. And we would like to see what role an inductor plays and what role a capacitor plays. So for an inductor, we decided that if I is constant, right, if I is constant, so we have waited a long time, like in here, and the current has become constant. If the current is constant, then the voltage is 0. And the only device that guarantees a 0 volt difference is a short circuit. So we say L is equivalent to a short circuit. And for capacitors, we saw that it was the other way around. If the voltage on the capacitor has become constant, so we have waited, all the transients have died away, and then C dV over dt is 0, so I is 0. All right? When I is 0, what kind of device can guarantee a 0 current? That would be an open circuit. So we say if V is constant, then the capacitor acts as an open. Okay? So the first row is important when there's a switching event, some sort of transient, and the second row is important when we have waited, we're trying to look for final values in the circuit. Remember, we always want to look for Y infinity, right? There's a final value of a voltage or a current or something. So the second row is handy for those cases. All right, very good. So with this, now we are ready to go over some more inductor properties. So let's go to the next page and see what we should do here. Okay, now change the color. All right, so the next property of inductors that we're going to look at is the energy. So energy in inductors. So just the way we can store energy in the electric field inside the capacitor. So we put some charge here, we got an electric field, we have energy. We can also store energy in the magnetic field of an inductor. So if you have an inductor and I pass a current through it, it generates a magnetic field. That magnetic field actually has energy in it. So to calculate the energy in an inductor, what we do is we start with the definition of power. Remember, we calculated power as V of t times I of t. This was true for any device, right? Doesn't matter what it is. For any device or any circuit, we have a voltage and we have a corresponding current. The product of these two tells us how much power is going to that circuit. Okay, so let's do that. And here's our good old inductor. I of t here, V of t here, and L. You may be wondering why I'm using lowercase here. It doesn't matter, lowercase, uppercase. And then I'm interested in energy, and I know that energy is integral of power with respect to time from some 0 to some t, right? So we'll go ahead and integrate this. Integral of 0 to t. P is V of t, I of t. Now I know that for an inductor, it just happens that we have this. So why don't we replace for a V from this equation into this equation into this equation? So I have L di over dt times I times dt. Okay, and now you can see that what we have here is this L comes out, you can cross this dt with this dt, and you have I di, so that becomes 1/2 of I squared. So we have 1/2 of L I squared of t. So the amount of energy stored in an inductor is given by 1/2 times the inductance times the current at that moment through the inductor, squared. For a capacitor, we had 1/2 CV squared. It was 1/2 times the capacitance times the voltage across the capacitor at that moment squared. Okay, so that's the simple equation that we have. Okay, so that's one little point that we need to know. And the next property relates to inductors in series. So we have found the series combination of resistors and capacitors, etc. So now it makes sense to look at the series and parallel combinations of inductors as well. All right, so not a problem. Let's draw a bunch of inductors here. L1, L2, L3. It doesn't matter really how many you draw. And I would like to find the equivalent inductance, right? This whole thing still has two terminals, so I can put it in a black box, and I can say that this black box has probably some equivalent inductance. And the question is, how much is that in terms of L1, L2, L3, etc. All right, not a problem. So ordinarily what we do is we apply a voltage between these two terminals. We call it Vx, and we have a current Ix. If I can find Vx in terms of Ix or Ix in terms of Vx, and I can simplify that to an equation that resembles that of inductors, I can find the equivalent inductance. Okay, so I have a current Ix flowing through all of these. These are in series, so by definition they carry the same current. How much is this voltage from here to here? The voltage across L1. Well, we know that the voltage across an inductor is given by L di over dt. And I is indeed going from high potential to low potential, so I do not need a negative sign. So the voltage across L1 is L1 dix over dt. How about the voltage across L2? Same thing, right? So here we have L2 dix over dt and so on, right? So I found this voltage, I found this voltage, I found this voltage, and so on. Now I can write the KVL. I can say this voltage is equal to this, etc. So I can say, I write the KVL, we have Vx is equal to L1 dix over dt plus L2 dix over dt, etc. These are all Ix because the current flows through all of them in the same form. If they are in series, they have to have the same current. Now you can see something going on here, right? So we can factor dix over dt. So we have L1 plus L2, etc. dix over dt. Does this equation look familiar? We have a two-terminal device, this box here, whose voltage is given by the derivative of the current that flows through it multiplied by some amount. So what would you call that amount? That would be the equivalent inductance of the circuit, right? So we say L EQ is equal to L1 plus L2, etc. So we see that when inductors are placed in series, they add, and that's similar to the case of resistors, right? When resistors are placed in series, they also add. Okay, how about inductors in parallel? So let's change the color and look at inductors in parallel. Okay, so here's the situation. We can draw it for as many inductors as you want. Let's just draw it for 2 for simplicity. So two devices in parallel by definition must share both of these terminals, right? These terminals are shared, or these terminals are shared. How do I find this inductance? Same method, right? So we apply a voltage, Vx, and find this Ix. All right, our hope is that the relationship between Vx and Ix resembles that of an inductor. All right, so how much is the current to L1? This current here. So that's the quiz of the day. I will give you 1 minute to think about it, all right? All right, so what did you get? Well, we see that the voltage across L1 happens to be Vx, right? These are all in parallel. So if I have the voltage across an inductor, I can find this current, right? So this current would be 1 over L1 integral of Vx dt. Similarly, this is 1 over L2 integral of Vx dt. And I know that this current plus this current will be equal to Ix. So I can say Ix is equal to 1 over L1 plus 1 over L2 integral of Vx dt. Does this equation look familiar? Sure, we said that the current through an inductor is equal to 1 over the inductance times the integral of the voltage. So this has to be 1 over the inductance. So we say 1 over Leq is 1 over L1 plus 1 over L2. The same equation that we have for resistors in parallel. So it's similar. I will see you next time.